Hello, so now we continue the course and talk about the primary damage production from many-body nuclear collisions. This first video mainly deals with the molecular dynamics methods describing how it can be used to simulate this effect. So this is sort of a repetition of what already has been said earlier on this course. We have an ion coming in on a material, it moves to some depth. This depth is determined by the electronic and nuclear stopping powers, but eventually the nuclear stopping power starts to dominate and one gets this set of many-body collisions between atoms. And in this regime, the ion energies are ion energy, and the energy of the recoils is typically a few electrovolts, so well below these kilo electrovolt energies or mega electrovolt energies where the ion radiations start. And at these low energies, one typically has a complex set of many body collisions going on at the same time. So this is no longer binary collisions, but really many atoms interacting with each other, including the chemical interactions, and this can result to quite complex phenomena. And basically this whole section, section 5 on the course, is telling about what the end result of this complex phenomena may be. So still a little bit more detail about the physics and about the timescales of what's going on. So in the beginning we have the linear collision cascade, which is the ballistic phase. This is what the binary collision approximation can describe. This phase lasts about 0.1, 0.2 picoseconds, are really never much longer than 0.2 picoseconds. But then after that one has this set of many-body collisions, which is often also called a heat spike. And from the heat spike many-body collisions, one finally gets the remaining primary damage. And this has, after the heat spike, everything has cooled down, the extra thermal energy has vanished elsewhere. We are left with some defects, and this has happened in about 100 picoseconds. In many materials, actually faster than that, 5 to 10 picoseconds. And this is what's called the primary damage from a single cascade. Then after that, there are many other things going on. The defects can be mobile due to thermal migration. If there is overlapping irradiation, one can get many other effects, production of dislocation, phase changes, amorphization, and so on. And if one looks on a larger scale, if there is any stress or strain in the system, the dislocations may be mobile, and this can further affect the damage evolution. These latter stages will be dealt more in other sections of the course, so this section 5 deals with these three stages, from the linear collision cascade via the heat spikes into the remaining primary damage. And as I said a moment ago, this first video deals mainly with section 5.2, which is about how to simulate that with what's known as the molecular dynamics method. So the previous section of the course dealt with the binary collision approximation and the binary collision approximation simulation method. Now we deal with molecular dynamics, which is fundamentally completely different the way the algorithms are set up from the BCA method. Well, the molecular dynamics method is actually quite a big use. Some people call it an industry. There are literally tens of thousands of people doing molecular dynamics in the world for various fields of materials physics, chemistry, and biochemistry. And many of these simulations have absolutely nothing to do with radiation effects. So radiation effects molecular dynamics is just a small subset of all the molecular dynamics work going on. If you forget about the radiation damage for a moment, here is a very simple illustration of what molecular dynamics can be like. This is simulation of atom motion in copper at 600 kelvins. So this is about 300 degrees C. So each sphere here is a copper atom, and the temperature is about 300 degrees C. So this is if you take a copper pan and put it in your oven at maximum temperature and could look at the atom motion on a femtosecond time scale, this is pretty exactly what the copper atom motion would look like. Well, if you ask me, simulation that is particularly boring, just atoms vibrating a little bit. There is no new physics either in that kind of a simulation. So the interesting part comes when we start simulating radiation effects. But on this course, before we start showing you results on this, we'll describe how to do this properly with molecular dynamics. Well, the molecular dynamics method, it's about the same age as the binary collision approximation method. It was originally developed by Alder and Wainwright in 1957 to simulate atom vibrations in molecules. And this is where the name molecular comes from. This name is now in retrospect unfortunate because typically materials physics molecular dynamics does not involve any molecules. It just only involves atoms in a crystal or amorphous material. But the name has stuck, so everybody calls it molecular dynamics anyway. Well, then after that, one of the very first uses of molecular dynamics in a larger system than a couple of atoms in a molecule was in 1960 by Gibson, who used it to simulate radiation effects in solids. So what he and his collaborators did is they had a atom which got a recoil energy, and it moved a little bit, collided with a few other atoms, and these trajectories here are showing how the atoms were moving in this very small system. And by current standards, I mean, this was very primitive simulations that potentials were purely repulsive and so on, but they did actually get one effect physically correct. They saw that if one atom collides with the next atom, this may collide with the next atom, and this with the third atom, so you can have a sequence of collision, what's known as a replacement collision sequence or a linear collision sequence. And actually, it was quite amazing if you think about 1960. There were no modern silicon chip computers. The computers were still working on vacuum tubes. They were huge, they were complicated, but still they managed to do this simulation already back then. Well, since then these methods have different simulation methods have of course been used widely to simulate radiation effects. But to get an idea of the historic development, I did a literature analysis about this in 2019. I simulated looking at radiation, the keyword radiation in Web of Science, and then several different simulation methods. And this upper plot shows the 5 most used simulation methods with respect to radiation. We take in order this blue graph here, down here, is the binary collision approximation method. If you look closely, you see that it's still around 1990. It was more or less the most dominant method, but since then its use has been increasing, but much less rapidly than the other methods. And then we have finite elements, which we won't discuss much on this course. Then we have Monte Carlo simulations on neutronics. This was mentioned in the neutronics section of the course earlier on to some extent. Then there is density functional theory, a quantum mechanical method, which will be mentioned a few times during this course. But the most used method since 1990 until now is the molecular dynamics method, which, as you see in recent years, since 2015, there have been something like 500 publications per year related to molecular dynamics and radiation effects. So this is the motivation why we now spend a good deal of time describing the molecular dynamics method for radiation effects. So to get more scientific, the molecular dynamics algorithm is actually, the basic idea is very simple. So what you do is you set the initial conditions, you give atoms initial positions and initial velocities, and then choose a short time step delta t over which you iterate. Then this is the crucial physics input in molecular dynamics. You get the forces acting between atoms. And this can be done either classically by taking a potential energy function and getting the gradient, the derivative of it in 3 dimensions. And this gives the forces if it's an classical analytical potential. Or alternatively, you can get it from a quantum mechanical simulation like DFT as part of the DFT algorithms. And then when you have the forces, the physics input is there. and the rest is basically numerical mathematics. So after you have the forces, you get the acceleration using Newton's law. This really is this trivial. You just take the forces and divide with mass, and that gives you, of course, accelerations. But then you start moving the atoms, and this is this crucial idea in molecular dynamics. Take this short time step delta t, then move the atoms depending on which velocity they have and which acceleration they have. And so you take the velocity times delta t, 1/2 the acceleration times delta t squared, add this to the current position, and this gives you the new position. And these equations are, of course, familiar from high school physics. So this is the very basic kinematic equations. So there is nothing mystical here. And in principle, molecular dynamics works with only this step. But then in practice, it's rather inaccurate, and by adding just a couple of correction terms or a few more, one can get it much more accurate. So usually there are correction terms, but they don't really add anything to the basic idea. And then you do the similar thing with velocities, also with the basic trivial equation, and then some more accurate correction terms. Then you move the time forward by this delta t, and this is just a very similar linear scalar operation, and then you repeat. So the basic idea, as I said, is very simple. You get the forces in the new positions, get the accelerations in the new positions, then you again solve the equations of motion, move the time forward again, and then you keep doing this. And you realize that in principle one can get as far in time as possible, but on the other hand, this size of this time step obviously limits how far you can get in practice. So getting the time step is a crucial part of this molecular dynamics. And this relates to numerical solution of differential equations. And the short answer is that the time step is too long, the system explodes. I mean, for instance, in this GR5 algorithm, in this test, if the time step was 10 femtoseconds, energy wasn't conserved at all. The energy explodes to some crazy values. Another algorithm with the velocity where 10 femtoseconds is initially unstable. After that, it more or less stabilizes, but the fluctuations are pretty large. But then you see that the accuracy increases well with the time step. So 8 femtoseconds is still inaccurate in GR5, but 6 femtoseconds is almost accurate already, and 4 and 2 are actually extremely accurate time steps already. Of course, you don't want to make the time step unnecessarily short, because you need to iterate over the time step. So if it's too short, you'll also get into trouble. Well, there is also a pretty good rule of thumb for what's a suitable time step. Consider the fastest moving atom in a system, and then say that this fastest atom shouldn't move more than 1/20th of the smallest interatomic distance per time step. And typical interatomic distances in solids and molecules are like 1 or 2 angstroms. So if it's say 2 angstrom in say silicon or copper, then this limit of motion would be about 0.1 angstrom. This here isn't any strict mathematical statement. This just comes from experience from doing tests like this to get this rule of thumb. But the downside or conclusion one can do from this is that the faster the atoms are moving, the shorter the time step needs to be. And it turns out that even though in equilibrium, like here, the time step can be of the order of femtoseconds, if you have a high energy atom from a radiation effect, you can need to go down to much shorter time steps, sometimes even of the order of attoseconds, which obviously will slow the simulations down. Well, this is then some more technical details on molecular dynamics. So first of all, if you want to simulate a bulk material, not a nanostructure, but a bulk material, bulk matters, of course, has huge amount of atoms. 1 cubic centimeter copper has 2 times 10 to the power 22 atoms. So this obviously would be too much even for present-day computers. But there is a smart solution to simulate these to avoid any boundary condition. This is known as the periodic boundary conditions. This means that if an atom is at the edge of a simulation cell, if it moves over the boundary, you put it back on the other side. And this is just a simple operation of this is the x coordinate, if it crosses the border, add the simulation size to the x coordinate, and then it gets here. Then, of course, atoms can also interact over the boundary. So if you have an atom here and an image atom here, they should interact over the periodic boundaries over here. But there is a simple mathematical equation for doing that. And we won't go into that, but if you look into any molecular dynamics textbook, all the molecular dynamics lecture notes, which are also available in our department, you will find this material. Well, there are alternatives. There are open boundary conditions. Of course, you just let atoms fly freely into the vacuum. This means that the algorithms don't need to be modified in any way. You can fix atoms. This is always unrealistic in the sense that in reality there are no fixed atoms in the real world. But sometimes it's still a useful simulation trick, for instance, to prevent a cell phone starting to move. Then one can do still reflective boundaries, that atoms are reflected off a boundary like it would be a mirror, but with these one has to be careful, because if you do that, the momentum is not conserved, and this can lead to troubles in many simulations, so one should be careful about reflective boundaries. But then what's important is that these four kinds of boundaries, periodic, open, fixed, and reflective, they can be combined in different dimensions. So you can have, for instance, periodic boundaries in two directions and walls in two directions, or periodic boundaries in 2 dimensions, 4 phases, and then open boundaries here, which would correspond to a thin film up to a vacuum. Well, then in many molecular dynamic simulations, there is what's known as temperature or pressure control. So if you want to simulate in thermodynamic equilibrium a system with the constant temperature, then you simulate the NVT and thermodynamic ensemble and control the temperature. If you have that constant pressure, then you can similarly simulate the NPT using a pressure control algorithm and also temperature control. But now that we are interested in radiation simulations, it's very important to understand that this business here corresponds to an equilibrium thermodynamic ensemble. An equilibrium in thermodynamics means that atoms have time to vibrate long enough to reach local equilibrium, which is typically at least a few hundred femtoseconds. Now, a moment ago, I told you that the binary collision approximation, the linear collision cascades, happens faster than a few hundred femtoseconds. So this means that in a binary collision or linear collision cascade, there is no thermodynamic equilibrium. The system is actually, in the beginning of a binary collision phase of a collision cascade, the system is not a thermodynamic system at all, because there isn't enough time for thermodynamic relaxation with the environment, because the atoms are moving faster than the thermal, much faster than thermal motion. And because of this, it's very important not to use either of these in the collisional phase of a radiation simulation. The only correct way to do it is to simulate the NV ensemble, which means that simply means that you don't do any temperature or pressure control. You just use the core MD algorithm and nothing else. So that's the first thing to keep in mind for radiation MD. But this is not enough. It turns out that if you take the standard MD algorithm and start to simulate radiation effects, you almost always go wrong, and sometimes horribly wrong. But because of that, a few groups in the world have over the last 25 years or so developed augmentation methods to molecular dynamics to handle this. And here I'll discuss the most central ones, which are now commonly accepted by everybody in the field to be appropriate. So first of all, in equilibrium molecular dynamics, atoms are always moving only near the equilibrium potential well. But in high energy collisions, like in the binary collision, we are actually in this repulsive part here. Okay, now the drawing looks horrible, but it is actually more or less a smooth line. This is exactly the ZBL potential which was described in the previous section of this course. This can be used to a fairly good accuracy to simulate the high energy effect. And DFT can be used to simulate this even more accurately. If you're interested, you can check out this reference here, which set it up by comparing with even more accurate methods than DFT. So what one needs to do is one needs to have not only the equilibrium part, but also this high energy repulsive part realistic in radiation molecular dynamics. And this is just to illustrate the difference of chemistry and material science and then radiation physics. Then there is the energy electronic stopping power. Now, in the previous section, you have heard a lot about electronic stopping power, so no need to repeat it. But let me just mention that this electronic stopping power can be added as a frictional force in molecular dynamics. So this is simply the basic approach is simple. Take the high energy atoms, which are either the ion or the colliding atoms, which are receive the high energy, and then apply the electronic stopping power on these atoms as a frictional force. And this is basically the same approach as adding electronic stopping to BCA simulations, but in molecular dynamics you need to do it every time step of the atom motion. Well, the nice thing about this is that one can figure out whether it works by comparing with experiments. And this has been done by our group and a few other groups in the world. And we can find that with a good enough electronic stopping model, you can reproduce experimental range profiles quite accurately. And again, we won't go into details in this course, but there is a few references you can check if you're interested in the details. But then there's one part which is a bit tricky and where there are many different solutions depending on case, is how to deal the boundaries of the system. Just told that the collisional phase should be simulated with the plane NVE. But then still, if a system is finite, is part of a bigger system, then one would want to do something else elsewhere. And here is a few cases which illustrate what can be done. So if an ion impacting our surface, this part here needs to be free MD, so this would be the NVE ensemble. But then one can have temperature control outside this region where the heavy collisions occur, and one can have fixed atoms at the bottom. Otherwise, the momentum coming from the ion would put everything into motion. Then if you want to simulate the bulk system, it's basically the same thing, except there is no free boundary, but you do scaling in all dimensions. And also you probably want to scale the momentum of the total momentum of the system to zero. Then for swift heavy ions, one probably wants to do something like this. So you have the swift heavy ion giving kinetic energy to the atoms, but then have free molecular dynamics here, and then have atom scaling at the edges. Also, if there is lower energy collisions from the swift heavy ion, you want to include them in the you may also assign velocity to some of the atoms by the high energy recoil by simulating it explicitly. And KC is the simplest. If you simulate radiation of free nanocluster in vacuum, then you don't need any boundary conditions at all. Then you just make the nanocluster and simulate everything directly with the basic molecular dynamics algorithm, and this is perfectly realistic. And for a nanowire, one may want to do this, that you simulate the ion impact with free MD, but then have temperature control in only one dimension of the system. And finally, I mentioned already the issue of the repulsive part and the equilibrium part. Of course, these two need to be joined, and there needs to be some smooth joining of the two systems. This is some sort of interpolation scheme is needed here. Two schemes which are mostly used. One is a Fermi function, where a Fermi function is used as an interpolation function, and the other one is simply to take a cubic or fifth order spline function and match the potential and its derivative with the spline function. But one very important thing here is that because we deal with radiation effects, chemical bonds can break and reform, and almost always do break and reform. So one can't use any interatomic potential. One needs so-called reactive interatomic potentials which allow for this. And the reason I emphasize this is that molecular mechanics for molecules, for instance, with so-called force field, molecular mechanics force field, most force fields are not reactive at all. In them, a covalent bond cannot break. And obviously one should absolutely not use this kind of force fields to simulate radiation effects. And this pretty much finishes what I wanted to say about molecular dynamics on this course. Let me just emphasize that this interatomic potential choice is really, really important. And this is a big issue of how to make good molecular dynamics interatomic potentials. There is no automatic way of making them which anybody has ever developed, which would really work in a transferable way. But fortunately, people have been doing this since the 1960s systematically, and by now, for almost all pure elements, one finds a potential, at least pure elements of any practical use, like silicon, germanium, carbon, copper, iron, gold, and so on. Almost all common pure elements have good potentials. Many common compounds have potentials as well. Say gallium arsenide, gallium nitride has several potentials which have been found to work pretty well. But what is reliable is not so easy to tell, and one really needs to be an expert in the field to be able to assess this easily, or then do a lot of testing yourself if you don't have experts available. But let me just mention still a very important classification. If you use any kind of interatomic potential, then the method can be called classical potential molecular dynamics, or maybe force field molecular dynamics. And these classical potentials are quite often, they are very efficient, and one can do MD up to hundreds of millions of atoms. But even these classical potentials have a subdivision, which has become more important in the last 5 years or so. The original classical potentials were all analytical functional forms where you fit some parameters, or maybe used cubic splines, but in any way then it's still a third order polynomial, and this can be called analytical potential molecular dynamics. More recently, people started using machine learning, for instance, neural network, Gaussian progress regression, and so on, other machine learning tools. Then there isn't really any analytical form. One cannot write out some equations on pen and paper which would describe the potential, and then these potentials can be called, for instance, machine learning interatomic potentials. And these are usually, they are not automatically better. You can go horribly wrong also with a machine learned potential, but they are usually better than the classical potentials because there are many more degrees of freedom. On the other hand, they are almost always slower than the analytical potentials. And there isn't actually a very strict limit here. From some machine learning potentials, one can simplify them to, in the end, become essentially an analytical potential again. But the other big class of molecular dynamics is that done quantum mechanically. That is, you can use density functional theory and other quantum mechanical electronic structure calculation methods which solve some Schrödinger-like equations, and then one can get the forces from these and then do molecular dynamics based on these. And then the method can be called density functional theory molecular dynamics, or quantum molecular dynamics, or ab initio molecular dynamics, depending what you like. These are, of course, much more reliable than the classical potentials, but the problem is they are also much slower. So whereas Classical MD can you can even on a single laptop you can easily do millions of atoms nowadays. With DFT, you are limited to more or less system sizes around 1,000 atoms. On a laptop, you could maybe do 100 or 200 atoms. But here I'll finish this short overview of MD. This was clearly not enough to teach somebody to do MD simulations. This was just emphasizing the key parts which are necessary to understand MD of radiation effects. So if you are more interested in MD, we have a course on it at our department, and also there are many molecular dynamics courses around the world, and textbook, of course. And finally, before we go on to the next videos, I'll just mention one thing, that when we show molecular dynamics of radiation effects, we quite often, the actual simulation is a full 3D simulation, but to illustrate it, it's easier sort of to look inside the material by making a 2D cross-section. So just for the plotting, you cut out a 2D cross-section, typically it's a few atom layers thick, and leave out the rest and only plot what's here. And just to give you a flavor, this will be repeated in the next video. This here is an illustration of one of the molecular dynamics cases of a cross-section of just a few atoms. This is actually a density function of molecular dynamics or recoil in silicon, and showing how it went. But yeah, that was this video, and then we'll continue from here in the next video, showing many of these MD results of radiation effects.